Okay, folks, we're going to review this section on the ratio test. And the ratio test is kind of a result of the geometric test. There's a little proof on it, but I'm going to skip the proof for right now. But and it has to do with the fact that if your R value is less than 1, then you certainly have convergence. And so if we take the ratio of, if we use the ratio test to determine convergence, the test will tell us if the series converges. If we, for step 1, if it's a series of non-zero terms, then if the ratio, the limit of the ratio a sub n plus 1 over a sub n is less than 1, then the series converges. If it's greater than 1, the series diverges. If it's equal to 1, then it's inconclusive as a test. The ratio test is particularly useful for a series that converges rapidly, such as those involving exponents, factorials, nth powers, or things like that. The creator of this test, or the origin of it, is from France by a gentleman named Jean Laurent d'Alembert. And so he, in the 1700s, I think it was about 1750s or so, something like that. So a lot was going on in the Age of Enlightenment at that time, but he was a French mathematician, a physicist, a philosopher, a music theorist, and he, together with other mathematicians of the time, surmised that these infinite series were extremely beneficial in determining the behavior of functions, so as you will see. But anyhow, so back to our work here. See you later, Jean, and then we'll do a couple problems. So we'll start off with the first example, where we have the summation or the series from 0 to infinity of 2 to the n over n factorial. So remember, we're going to take the limit as n approaches a sub n plus 1 over a sub n. And so we set that up in the first step here. And then I'm going to multiply by the reciprocal. And with that, we're going to do a little bit of work with that. Let me go off here and go back in. So we're going to manipulate this a little bit. So then we have the limit as n goes to infinity of, I'm going to make this a 2 to the n times 2 to the first power. And then I'm going to move terms around. So remember, with a fraction, you have products that you multiply straight across, like so. So we can change the order. So I'm going to pull that 2 to the n over here. And then I'm going to multiply by n factorial over. And remember, n plus 1 factorial is just n plus 1 times n factorial. So we'll be able to cancel the n factorials there. So once we do, we cancel the n factorials here. Here, those become 1s. And then we cancel the 2 to the n power there. And so what do we get? We have the limit, just to be clear, as n approaches infinity of 2 over n plus 1. So that's going to turn out to be 0. And that's less than 1. Therefore, the series converges. So the series converges by the ratio test. Okay, and remember, when it's less than 1, what I have checked up there, it's going to converge. The limit will tell you that the series will converge. So this first one converges. Okay, now the next one, we've got the infinite series n squared times 2 to the n plus 1 over 3 to the n. And so what I've done is I've just skipped to the product of the reciprocal, multiplying by the reciprocal here. So then I started to manipulate this. So remember, put in the a sub n plus 1, put in n plus 1. And then over the a sub n. So I've got that, and I multiply by the reciprocal. Now I'm moving all the n plus 1s as squares over top of each other. And then I've got 3 to the n's. And then 3 to the n times 3, because 3 to the n plus 1. And then I've got the 2 to the n plus 1 with the 2 to the n plus 1. They cancel. So then it turns out I get the limit as n approaches infinity of n plus 1 squared. So why don't we just go ahead and square that? Pretty easy just to square to get the n squared plus 2n plus 1. And that would be then over n squared. And then I've got an extra factor of 2, right? So I've got a 2, and do I have a 2 and a 3, right? So it's not really going to matter there. So you can see that the limit as it goes to infinity of this expression, we use the limit product rule. So we're going to the limit of the n squared fraction. That's just going to be 1, n squared plus 2n plus 1 over n squared. That's going to be 1 times 2/3. So it's equal to 2/3, which is less than 1. Therefore, the series converges by the ratio test. Duplicate that over here. So this series also converges. When the 2/3 is less than 1, we're good to go. It converges. Okay, then we have 2 more that I wanted to go over. So if you look at the first one, I went ahead and set up the ratio test, and it turns out that with the first term, let me get a yellow highlighter here. So I've got the n plus 1 here, and then I've also got this a sub n, but it's the reciprocal of a sub n. And then I began to start canceling things. Remember, I wrote n plus 1 factorial is n plus 1 times n factorial. And so everything is canceled but what you see in this step. So when you look at that, I rewrote it. Now, you might think, I'll go inside and I'll take the limit of the inside and then raise it to the nth power. But you can't do that. In fact, that would produce an indeterminate form. You're thinking it's going to be 1, right? But it would produce the 1 to the infinite power, which you know is indeterminate. Or maybe you knew at one time and you might have forgotten, but it's indeterminate. Now, if you look at this, I can manipulate this and you'll go, oh, aha, I think I know what this is. That I've got this, this is going to be 1 plus 1 over n. It's starting to look like something that I know. And here's what it is. It's E. And that's greater than 1. Therefore, the series diverges by the ratio test. So the series diverges by the ratio test. Now, I was going to do a little thing about how you could find out what in the world is going on. How is this y equal to e? If y is equal to 1 plus 1 over n to the nth power, and then you take ln of y is equal to ln of 1 plus 1 over n to the nth power. So you end up with ln of y is equal to n times ln of 1 plus 1 over n. And I'm going to challenge you to take a look at this then and to take some limits. And what you're going to find out, the limit as n goes to infinity with this, you will get e, but you're going to have to do a couple of manipulations on there. I just want to challenge you that maybe you want to try that tonight or today, and I'll come back with you in class with that solution if you don't remember it or you want to go back and review it. Okay? All right, so that's it for that one. That one diverges. Then one more that we have to do is here. So we've got this. We've got the series. It's an alternating series of square root of n over n plus 1. Now, to me, if I look at this, I think it might or might not converge. It's really hard for me to tell, but I'm going to think maybe it will. So we're going to do the ratio test on this, but the results are kind of weird with this. It is an alternating series, right? So let's do the ratio test, see where it gets us. So I've got the first step laid out here and then on the second step, I think you can see a sub n plus 1 times the reciprocal of a sub n, right? And I move like terms together. So you can kind of see what we have here. It looks like the limit of, I'm going to bring this first one together. As n goes to infinity, I'm going to use the quotient of n plus 1. Now remember, unlike the last problem, we had n as the exponent right here. I have a constant n plus 1 over n to the 1/2 power here. So I can go on the inside of this limit if I wanted to. So I'm just going to put this n plus 1 over n plus 2. And let's move with this one by saying this is equal to the limit as n approaches infinity you can't put it right in there because it's not going to make sense. You're going to get infinity over infinity. So, but when you go 1 plus 1 over n times n plus 1 over n plus 2, then you're ready to go. In fact, don't you just get the square root of 1 times 1, which is 1. So the ratio test is inconclusive. But I'm sure some of you, inconclusive, are thinking, I don't know, Miss Allen, but I sure think something's up my sleeve, because I look at that's an alternating series, right? So the ratio test is inconclusive, but we're not done yet, right? So let's look at our a sub n, right? Our a sub n is equal to the square root. My line disappeared there. Let's say this. The ratio test is inconclusive, which is kind of part of our answer here, but we want to answer the question fully. Square root of n over n plus 1, right? There it is, right? So what I want to do with this is I want to say, how about this? How about the AST, the alternating series test? So step 1 for the alternating series test, I'm going to say, well, let's take the limit as n approaches infinity of n square root of n over n plus 1. Now, normally when you're dealing with rational functions, you're dealing with exponent powers. Like you have an n to the 1/2 in the numerator over. So you're going to look at this and you're going to say, as n goes to infinity, you're going to buy in fact that this is going to be, absolutely, is going to be 0. Check. Now, you could prove it if you wanted to. And then the second part, too, you're going to say, all right, well, the square root of n plus 1, the a sub n plus 1 term must be less than or equal to the a sub n term. So then we have in the bottom, we're going to have n plus 2. And then down here, we have an n plus 1. Now, if you want to see my proof of this, I know you're dying to see it. It's so cool. Anyway, when we have these two, we could say, well, by golly, it didn't work with the ratio test, but the series converges. Therefore, the series converges by the alternating series test. Okay, so alternating series test is what won the game for us. So you sometimes have your choice as to which one you want to use. You want to use the ratio test, you want to use the alternating series test, maybe the integral test in some cases. You have 10 tests now by which to choose, but that's number 4. That wins the game for us. Tomorrow, if you want, remember I said this was on our Schoology in the lesson 8.6, day 2. And this, 8.6, day 1 maybe. And you see a little photograph of my board work where I proved that second statement in the AST, alternating series test. Okay, that's it for today, and you guys have a great day. There's Jean Lemon. How do you say his name? Jean Laurent de Lambert. Thank you very much for the alternating, for the ratio test for this. It's been a great benefit to all of us. Kind of fun sometimes too. All right, you guys take care. I'll see you when I see you. Allen out.